I can start? So let's restart. So we saw this morning that taking the example of space charge, either direct space charge, meaning without a beam pipe, or indirect space charge, meaning that there is a beam pipe, but it is perfectly conducting and smooth. We introduced the concept of impedance. In this case, the interaction with the beam pipe is given by an impedance which is imaginary. As it is imaginary times this J, it is a real part, and there is a near real tune shift. But as I said, it was just to introduce, but in the most general case of an interaction with a beam with any impedance, the impedance will be complex. It will be one part of the job of some people to compute this impedance, such that we can put the impedance on this formula for the simple case. In the most general case, it's much more complicated than this, but the physics is the same. You will have a real tune shift, an imaginary tune shift, and a rise time, tau. It will be always the case. Why? Because the impedance of a machine in longitudinal or in transverse is the sum of all the impedance over the ring seen by the beam. So you will have the beam pipe. You will see all the beam position monitors, the kickers, the collimators, etc., etc. All the discontinuities. So we are in contact with the interaction with the equipment group, and we ask to have the smoothest beam pipe as possible. We ask to have the better conducting pipes. We ask to remove and to reduce impedance. Okay? But the beam will be unstable, whatever you do. It is unstable. All accelerators, there is an instability. But maybe you will not see it. Why? If the rise time here is very long, exponential t over tau, what does it mean? When the time is tau, it means that the amplitude has been multiplied by exponential of 1, which is about 3. So, okay, it takes time for the exponential to increase. Okay? If the rise time is 10 minutes, and you stay 1 minute, 10 seconds, you will never see the instability. You have an instability, but it will not develop. Very important concept, okay? But then, you have several types of instabilities, and first you have to better characterize your instability to see which mitigation methods you can use, because sometimes one mitigation is good for one instability, but not good for another. No time to discuss in detail, but okay. So, two mitigation measures which are easy. Here, this is phase space, xx prime. I remind you, as Chris said, normally particles perform ellipse, but you can normalize to have, in fact, cycle. Okay? What do you do here? You measure at some position an x, you see that your beam is oscillating, and 90 degrees phase advance after, you have a kicker, and you kick the beam. You know that the beam is oscillating in this direction, so the kicker will give a kick in the other direction to put the beam closer. You do this 10, 20 times, and then the center of mass is there. This is what we call a transverse damper. We can do the same thing in longitudinal. But the most fundamental stabilization method is Landau damping, named after the Landau physicist. What does it mean here? Here we could also spend a lot of time. But the idea here is that we will avoid to have all the particles oscillating exactly at the same frequency. Why? Because due to the impedance and the force linked to it, there will be a driven, let's say, force, which will force all the particles to oscillate at the same frequency. But if you have a spread in frequency, and that if the force has a frequency which is inside the spread, the energy of this excitation will be absorbed incoherently in these particles, and the beam stabilized. This is the concept. Let's imagine a swing also. You have 3 swings with the same frequency. They use huge force on the bar. If they are not at the same frequency or same phase, you can have 0 force there. Fundamental concept. No time to discuss in detail, but just to say that this is Landau damping. So equation is the same as before. You start, let's say, like this. X double dot plus omega x square x is a coefficient times x bar. Here now it is not omega x 0 because all the particles here do not have the same. It is omega x. But you still look for something with omega c. You derive, you have omega x square minus omega c square equal times x. If x is proportional to exponential j omega ct times x bar. So then you have x, which is k over omega x square minus omega c square x bar. Okay? But then now you will integrate. You integrate x times a distribution of frequency omega x, and this term now will become x bar. So you integrate also here. You remove the x bar on the left and on the right, and you end up with this, what we call dispersion relation, which we have here. Meaning it is so in fact, now I have a distribution of frequency omega x. My particles are not oscillating at the same frequency. I have a distribution. So I need to integrate over rho of omega x divided by this, minus 1. It's equal to the complex frequency shift I had before. By the way, you can check that if this is 1, this is omega c minus omega x is 0, we recover the same result as before. But now we have this. And now let's just take as an example here the case of a Lorentzian distribution given by this formula. Delta omega x, delta is the half width at half maximum. You have a kind of a Gaussian going to infinity, but it's not a Gaussian, it's a Lorentzian with thick tails. But what is nice to see is that this integral now become 1 over omega c minus omega c minus j something. So you have an imaginary term coming. It is coming from this pole here, by the way. Mathematically, it can be strange. There is a pole, etc. But if you do this properly, you have also the residue theorem, and you can integrate, you know, all this. This is the trick. But physically, it means what? It means that you add a frequency here, and you put a spread in frequency such that the frequency is inside the incoherent frequencies. The energy is absorbed incoherently by the particle, and the beam is stabilized. Okay? You can solve it, and you find that the beam stability condition is that this half width at half maximum of the spread should be bigger than the instability growth rate, Vx. This is for Lorentzian distribution, going to infinity. In reality, the tails are not going to infinity because you have a beam pipe, etc. So you have finite tails. So the stability condition is slightly more complicated, and it includes also the Ux, which is the real term, but this is just to tell you roughly how it works. You can do the same now in longitudinal. You can define a longitudinal impedance which is proportional to the integral of the longitudinal force. You can apply it for, yes, by the way, maybe I should say this. Here I take a distribution in frequency, yes, but it is just to explain the physics rapidly. But then in reality, how do you generate this? The best method we have for the moment is to use octupole. So these are 8 poles in a magnet. Why? Because if you make the computation, you will see that the tune in an octupole depends on the amplitude of the particle. So depending on the amplitude in phase space, the particle will not have the same frequency. It's exactly what you want. By the way, now you could tell me, yes, but ideally, initially, we wanted to have the machine as linear as possible. And now you introduce nonlinearities to stabilize. Yes, but this is what we like to do because we want to have a linear machine to be sure that we understand well. And then we introduce just what we need of nonlinearities to stabilize the beam. Yeah, this is... So same thing in longitudinal impedance, and you can define the longitudinal space charge impedance, which is a negative inductance. Okay? So this is why I was saying before, if you have too much longitudinal impedance reducing the longitudinal tune, what you could do is inside your machine, you introduce on purpose an equipment showing an inductive contribution to the beam, such that this minus inductive or capacitive plus inductive gives a total impedance which is smaller. It has been tried 20 years ago in the US or in Japan, successfully or not. Why? Because when you introduce this inductive impedance, it's not purely inductive. You have a real part, and this real part creates an instability. So then you need to be aware of this, etc. As I say here, in general, the longitudinal impedance, again, will be a complex function of frequency, and is the sum of all the equipment of all your machines. So you can imagine I was responsible for the collective effects at CERN for 10 years, many people in the team, but you can imagine that a lot of people were working on how to describe the impedance model of all the machines, because each equipment of each machine has an impedance that you need to understand and characterize correctly. Okay, and by the way, a longitudinal impedance is a problem for the beam, but it is a problem also for the equipment. Because if you have a certain equipment which has not been designed well, and if you have a beam coming through it, through Joule effect, there will be some heating, Ri square, for instance, and the equipment can burn. We had some issues like this also in the past. So there is interest also in the equipment group to come and discuss with us each time they want to install something. Okay, now I stop with the blackboard. I don't know if you want to put the projector here also as well, but I will show pictures of the mechanism we just discussed, plus other things. So let's start with some pictures we just discussed. So I mentioned you that we have this transverse direct space charge, but let's compare to what a quadrupole is doing. If you look at a quadrupole like this, a proton beam coming to us, if you look at the force x versus x, you see that you have focusing here. If a particle is on the positive x, the force will move it to the left. If the particle is here, the force will move it to the right. It will be the opposite in vertical because a quadrupole is focusing in x, defocusing in y. But by putting them correctly, you can globally, okay. If you have what we assumed before, a uniform beam like this, in fact, you have this kind of thing. So you see, this is the opposite of a quadrupole because it is defocusing and it's a linear force. Remember, we had a linear force proportional to x. It's because it is a constant and uniform density here. If you would have a Gaussian, you have this linear part here, but at about 2 sigma, then you have a maximum and then it goes down. So the force is highly nonlinear. And if you want to do this properly for the beam, you have to take into account not only the center particle, but all the particles. If you do so, in the tuned diagram like this, Qx, Qy, this was initially my working point. The maximum shift is here for the central particle. But for all the other particles, they are here now. So you see, it occupies, due to the space charge, all the particles now will have different frequencies. It occupies a certain tune footprint that I have to accommodate in the tune diagram. So this tune footprint should not be too large. Otherwise, it will overlap on some resonance. And by the way, this footprint here is at 2D, Gaussian in X, Gaussian in Y. If you have also a Gaussian in longitudinal, you will also feel this space here, meaning that from the low intensity particle to the maximum tune shift, you have all these particles. Each dot here is a working point of a particle. Now, you have here something like this, and you have a resonance. So if you overlap with a resonance here or here, then you can have different regimes. Here, I just want to sketch this. This is here the small amplitude particles, and here you have the large amplitude particles, and you have two different regimes. If, in this case, it was a particular case in the PS machine, we overlap a resonance, it was a fourth order resonance, octupolar resonance here, with our tune footprint like this, we saw some emittance growth. If we overlap at this position here, due to the longitudinal motion, head to tail, we had some particle diffusing into a halo. Look at an example here. So we started with a tune footprint like this. The integer resonance is here. It's another case. Huh? Then I reduce the working point, so everything is going down, and we interact with this. Initially, we had this transverse profile. After, we have this one. Do you see a change? It's broader. So the emittance is sigma square over beta x is larger. Now the quality of your beam has been degraded because you want many particles in a small emittance. So if you have a case like this, you degrade the thing. If now in the second case, I was injecting a bunch, no instability, no losses, then I put an octupole on in the second case, and then we had some losses. And in the longitudinal profile, you see that initially it was a Gaussian, and now some tails or halo was created. Here again, not good at all. So you need to understand it well and model correctly all this and suppress maybe the resonance. Here, this is a bucket. So this is in longitudinal plane now, nanosecond in horizontal, MEV. This is the beam. And this is a bucket which is limited by the separatrix, which limit the stable and unstable area. Here it is just to represent that with space charge, in this case, the bucket is lower. And if the space charge will be higher, the bucket will be even lower, 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 until you don't have bucket anymore. I was mentioning this. This picture is a quite famous and a textbook picture. It's the first transverse instability we had in the LHC. We had a bunch, nominal bunch, 10 to 11. It was in 2010 or 2011. Nominal bunch, no transverse damper, no Landau damping, nothing. Wanted to accelerate this, and we lost it during the bump. Why? Because at some point it was predicted there will be no Landau damping and you have an instability. LHC, you do many turns, so the instability has time to develop. What do you measure here? This is the center of mass, what I call X bar before, as a function of time, during 120 seconds here. You see what each dot, each point here is the center of mass in the pickup. So the beam is going, it's one bunch, going through a pickup. You look at the center of mass, turn after, turn after, turn after, and you plot it. So of course it is symmetric up and down because of the integer, because of the tune, which is not an integer, by the way. And then at some point, the envelope, you see, there is a nice exponential. You just need to fit with the exponential t over tau, and then you deduce tau. In this case, tau was about 10 seconds, more or less as predicted. Okay? But don't forget that here you have the beam pipe here at some point. This is why here you lose the beam. Okay, this was just now to speak about transverse space charge, longitudinal space charge in coherent, single particle, or coherent, the beam as a whole, impedance in general, complex, with this formalism, coasting beam, etc. Now, if you want to use more involved mathematics, in reality, if you have a bunch in general, interacting with an impedance, any impedance, general one, but it's a complex function of frequency, you can solve this, you can do a self-consistent treatment of all the bunch beam coherent instabilities in transverse or longitudinal, including transverse damper and longitudinal damper, for any chromaticity, etc., etc. But for this, you need to use the Vlasov equation. So you start from the general case of a bunch interacting with an impedance, you use the Vlasov equation, you linearize the Vlasov equation, and you end up with an eigenvalue system to solve. Here, I spare you the mathematics, but you can see them on other lectures I give, in particular for the students of La Sapienza in Rome. And you have the delta Q, so the tune shift you are looking for, the complex tune shift normalized by the synchrotron tune, so you have kind of delta x, AX is equal to lambda x. But you have this AKL and AIJ, which has the eigenvectors you want to find. The matrix H here is the matrix you want to diagonalize. And once you have these eigenvectors here, you can you can put them here, and you got the eigenvector, the final eigenvector, which is linked to the intra-bunch motion. So eigenvalue system to solve, you have this matrix, which includes the effect of the impedance, the bunch intensity, the bunch length, the chromaticity, the transverse damper, all this is there in this matrix. So when you know the matrix, you solve the eigenvalue system by diagonalizing the matrix, and you find the delta Q over QS, which are the eigenvalues. The eigenvalues, you can plot them, real part and imaginary part, and if the imaginary part is negative, you have an instability, and you can see by how much. And as I said, the eigenvectors, they are useful because then you can have the eigenvector of your system, and the eigenvector can show you how the bunch is behaving, or the center of mass is behaving inside the bunch. It's very interesting. Why? Because it's an observable that you can have in the control room. What is the Vlasov equation? It's linked to the Liouville theorem. It expresses that, in fact, the beam is moving like an incompressible fluid in phase space. Okay? Why? Because here we assume no diffusion and no damping. Otherwise, you will go to Fokker-Planck equation. And Vlasov equation is you have a density or phase space density psi. It is just d psi over dt is 0. This is total differentiation because you follow the particles' canonical variables. But if you express it for a stationary observer around the wing, let's say at the pickup, beam position monitor, then you can use the partial derivatives versus time t and q and p, which are the canonical variables of the Hamiltonian that Chris was mentioning. So it's something like this. Okay. And if you do this, for instance, this is the kind of plot that you will obtain. So now much more complicated. In this approach, as it is written here, Now the motion of the beam is described not by a sum of all the particles, but it's described by a superposition of modes of oscillations rather than a collection of individual particles. So what we do in this case, because you solve the eigenvalue system numerically, you can plot this delta Q over Qs. So delta Q is the Q you are looking for, the tune, the new tune due to the perturbation, minus the initial tune, divided in transverse, divided by the synchrotron tune in longitudinal. And you plot it as a function of the intensity per bunch. You have one bunch, is the number of particles. You see the mode 0 here, starting with one line, and then many other modes, because in fact, as you have 2 degrees of freedom in phase space, amplitude and phase, the solution is characterized by 2 mode numbers. I don't go into detail, but these are called azimuthal and radial mode numbers. But this is why for each mode here, you have the mode 0, 1, 2, 3, 4. You have then several lines because then you have the radial modes. But what you see here, chromaticity is 0. Mode 0 is going down, and then it is coupling to one of the mode -1. You see some activity here, you have an instability. Then there is decoupling, coupling again, decoupling, and then the big instability is coming here. Okay? But again, all the physics is here. Huh? This is the real part. The imaginary part, absolute value here, tells you if there is an instability. And indeed, there is no instability here. Then there is a bit of instability, then 0 again, and this is... What is this value here? This value is the imaginary part of delta Q divided by Qs0. So it is linked to this V. So you can deduce the V and you can deduce the rise time of your instability. Huh? Depending on the intensity, you will have a certain rise time. Okay, so you see here, to arrive there, you need quite some mathematics and to understand what you are doing. Galactic is my Vlasov solver, and Pietel is a numerical code. So we had a very good benchmark. This is the eigenvalues here. The eigenvectors can help you to plot the signal turn after turn inside a beam position monitor, assuming it has infinite bandwidth. So indeed, your bunch is coming through a beam position monitor. You look slice by slice at the motion. So there is a trace, and one turn after, there is another trace, and you superimpose them. Why? Because if you superimpose them, you can see that you have some nodes here. And the nodes are characteristic of the mode number here. Again, I don't go into detail because it's quite involved, but just to show the power of the Vlasov equation and of the theory in this case, because all this is very general. What you see here is that all the eigenvectors, they are centered at what we call the chromatic frequency, which is playing a very important role for transverse instabilities, and they depend on chromaticity and sleep factor. So they are key parameters, meaning these are parameters you can play with to mitigate instabilities. Now, these are the intra-bunch motion at low intensity, meaning when all the modes can be let's say, considered independently. But it was discussed already a long time ago by Laclar. But when many modes are taken together, it was never done. I published a paper on this several years ago, but the main message I would like to show you, to convey here is that due to the mode coupling, or due to the fact that the modes will interact, the pictures of the intra-bunch motion like this would not be symmetric left-right. Left and right are head and tail, huh? Because you see they are perfectly symmetric left and right. But due to the interaction between the modes, you can have asymmetric pictures. And as we are observing a lot of asymmetric pictures now in measurements or simulations, I wanted to understand better from theory. And in fact, it's an extension and you need to include the mode coupling. But the take-home message for you is indeed, if you see some asymmetric pictures, this is certainly due to the fact that you have mode coupling. With space charge, with beam, with electron cloud. Because here, before, I consider a bunch interacting with any impedance. And the plot I showed you was for a certain impedance, but I can do this for any impedance. But the same formalism can be used also for space charge, for beam, or for electron cloud, which I will discuss after. By the way, you can do the same in longitudinal. You plot the tune as a function of the intensity. You see many modes coupling. And then you plot the bunch length as the function of the intensity. And you see also how it increases. First, linearly, because of some mechanism. And then you have the real instability starting. Again, this is another code, Vlasov solver of mine. I call galactic for transverse, galactic for longitudinal, and we compare two numerical things. Okay. Now let's move, we discuss space charge, we discuss impedance in general. Let's move to beam-beam. What is beam-beam? So here you have bunches crossing at an interaction point. Of course, the detector is here. Why do we put a crossing angle? We put a crossing angle because we have, in the LHC, because we have many bunches colliding. If we would not do so, there would be no crossing angle, you will have collision here, collisions here, collisions here, and then collisions which will not be recorded by the detector. We want to have collisions only here in the center of the detector, okay? Of course, if the spacing between the bunches is sufficiently large, there is no need to put a crossing angle, but here, for us, there is. But by doing a crossing angle, you see that the overlap is not perfect, meaning that you will lose in luminosity, okay? But okay, what do you see here? When this bunch here will cross this bunch, we are saying here 10 to 11 particles against 10 to 11. But what happened, by the way, most of the time? You have 10 to 11 particles crossing 10 to 11. What happens most of the time? They don't see each other. Most of the time, they just cross like this. On average, you have about 20 collisions, 20 events, which is not a lot. So most of the time, they just cross. But this proton sees this one, little kick, then the turn after, little kick, and so over time, some emittance growth. So this, you have to do this carefully because we stay sometimes 10 hours, 20 hours, okay? But here you have a beam pipe. Most of the time, the two beams are in different beam pipes, so they don't see each other. But around the IP here, around this place here, they share the same beam pipe. So this bunch here is seeing this bunch. This is what we call long range. This interaction here is called head-on, but they are seeing it. If the crossing angle is too small, in fact, the interaction, this one will give a kick to this one, and it will perturb the beam. So we need to study beam-beam head-on collisions, but also long-range collision. Okay, no time to discuss in detail, but the beam-beam is the interaction between the two counter-rotating beams. It's a Coulomb repulsion plus a magnetic attraction if it is PP, but for mu plus, mu minus, it will be Coulomb attraction plus magnetic attraction. Crossing angle, head-on, long range has to be taken into account. Here again, you will see that you have a nonlinear force, which is the same as space charge. And here again, you will have a spread and a tune footprint that you have to put in the tune diagram and avoid resonances. It does not disappear at high energy. The concept of Pac-Man is that at the beginning and at the end of the train, some bunches do not see another bunch, meaning that they will not have exactly the same number of long-range interactions, so there is some asymmetries, can create issues. And coherent modes can lead to loss of Landau damping. Why? Because if you have two bunches like this, they collide, they can oscillate either in phase or out of phase. You have two modes because you have two bunches. If you will have 10 bunches, you have 10 possible modes. And these two modes of oscillation, we measure them in the LHC. Amplitude as a function of frequency, this is the initial tune without beam-beam, and with beam-beam, you see two peaks here for the sigma and the pi mode. The sigma, the two bunches are oscillating at the same frequency, unperturbed mode. Pi mode, they oscillate at another frequency, but by the way, this frequency is far. And this here, if you have also the impedance there, maybe there will be an instability. And if this frequency is not in the spread of the incoherent frequency, you can lose Landau damping, because I remind you on the principle of Landau damping, you have an excitation at some frequency. If your particles have frequencies outside, there will be no Landau damping. So you see all the complexities here. And then, as I said before, tune as a function of intensity, or what we call here beam-beam parameter, which is similar to the space charge parameter. It's proportional to the brightness. You see that you have lines here in purple from the impedance. In green, this is the sigma mode and the pi mode, but when the beam-beam mode coupled with the impedance mode, you can have instabilities. So this is quite involved. Electron cloud, briefly. In blue here, this is a bunch. Here you have the beam pipe. You have a bunch here, protons, highly relativistic proton, and you have electrons due to some losses, or electrons created by photons due to synchrotron radiation. You have photoelectrons almost at rest. When the proton is coming, it attracts the electron, the electron will go and cross the vacuum chamber, hit the vacuum chamber. If the secondary emission yield of the vacuum chamber, let's say, is 2, 2 electrons will be created here. Slow electrons, they will drift. When the second bunch is coming, it will attract these 2 particles. They will collide, they will be go into the vacuum chamber, create 4 electrons, etc., etc. You have an avalanche effect. And after 10, 20, 30 bunches, you have a cloud of electrons inside the vacuum chamber. And then you have to study the interaction between your proton and your proton bunches and the electron cloud. So electron cloud, the electron cloud build-up is a multi-bunch but single-pass effect. You can observe it in transfer line between rings. We measured this between the PS and the SPS in the past. It can lead to coherent instabilities, coupling the different bunches or single bunch instabilities. Here again, there is a nonlinear force, so it creates a tune footprint in the tune diagram that you have to accommodate, and it does not disappear at high energy. By the way, it also induces some heating in the beam screen, and the beam screen needs to be cooled, and this is the limitation of the LHC. The LHC project has been approved in 1994. Electron cloud was not known. 1997, electron cloud started to be studied. Nevertheless, still as of today, it is the limitation that we have in the LHC. But fortunately, it's not important for muon collider. Okay, we have just one bunch. Even if you could have some instabilities sometimes with one bunch, but this is not our case here. But just for you to see for collective effects and beam dynamics in general, lesson learned from the LHC. This is a talk I gave at SLAC for the occasion of the retirement of the famous Alex Shao. Alex Shao is very well known in collective effects. He wrote this book, Physics of Collective Beam Instabilities in High Energy Accelerators. And he retired, and I was invited to give a talk there. And this is one of the slides where I said that in a machine like the LHC, not only all the mechanisms have to be understood separately, but all the possible interplays between the different phenomena had to be analyzed in detail. So we need to really understand well LHC, you need to have a good understanding of the beam coupling impedance, all the equipment around the accelerator. Driving detuning is something I did not discuss. It's more involved. You need to understand well the linear, nonlinear chromaticity, the transverse damper, you need to model it well. You need to understand well the Landau octupole and all the machine nonlinearities, space charge, the beam, long range head-on, electron cloud, the coupling, linear coupling strength between X and Y. Chris said this morning solenoid couple X and Y, but you have screw quadrupoles. And by definition, all the quadrupoles, when they are slightly tilted, they introduce some coupling between X and Y. The tune separation between the beam, etc., the noise, all this. Now, collective effects for the muon collider. So what are the challenges? So we need, as usual, to develop an impedance model for all the machines. So we started easily, let's say, with RCS, the 4 RCS. Why? Because there we have a lot of RF cavities with a huge impedance. So we consider them, plus the ceramic chamber due to the eddy currents but that we coated. All these are contributing a lot to the impedance. But then there will be all the rest. But we imagine that this dominates. And then in the collider, we took the beam pipe impedance and we scanned to have a correct, let's say, radius for the magnet. But okay, but it has to be done both in longitudinal and carefully, it takes years. And then to study all the related instabilities and all the mitigations. I remind you that each equipment of each accelerator has an impedance in longitudinal, in transverse, which needs to be characterized. It's a complex function of frequency and minimized. So we have iteration with equipment groups, vacuum chambers, RF cavities, etc. What are the mitigation methods? Transverse and longitudinal damper, chromaticity, Landau damping in longitudinal and in transverse, optics, because you can play with some optics parameters, you need to understand well. Space charge is an issue in particular for the proton driver, and you need to have a good understanding of space charge and of the resonance there and the interaction between the two, but also on the impedance, and also for the muons at low energy, both transverse and longitudinal. And the beam, because I remind you that at the end of the cooling, when we start already in the RLAs, recirculating Linux, you have one bunch mu plus, one bunch mu minus, counter-rotating, and we accelerate them while colliding in the RLAs, in the RCS1, in the RCS2, 3, 4, and in the... So each time there is beam-beam in addition during the acceleration. And in the acceleration, by the way, we had also a new regime in the RCS with a synchrotron tune bigger than 1. Normally, in most of the machines, it's about 10 to minus 3, meaning that you need many synchrotron oscillations to do one, or many turns around the machine to do one synchrotron oscillation. Whereas in this case, it was much bigger than 1, and we face some other complexities, let's say. Example of transverse instability studies done by David Amorim, who was a fellow with me, for the muon collider. So we participated, of course, in the design of the vacuum chamber, in particular, which radius could be allowed. He made some simulations about the emittance growth at the end compared to the, so emittance at the end compared to the initial emittance. Colored, when it is blue, it is good, yellow is not good, for different, let's say, chamber materials as a function of the chamber radius, for different transverse damper gain, transverse offset, and chromaticities. Just to say that you can scan all this and maybe conclude that if you can put your chromaticity at 2, use a 20-turn damper, then you can accept a radius of about 13 millimeters for the beam pipe. Example for the 4 RCS, he simulated the succession of 4 RCS, 1, 2, 3, 4, so from the beginning of RCS 1 until the end of RCS 4, and look at the sigma x, normalized, center of mass, and the losses. This is a case which is stable, but he looked at different transverse offset, damping time, chromaticities, etc., showing that in this case, we can go up to this offset for these parameters. But again, just examples. So all this has to be done. We know normally how to do this, but what we don't really know are the impedances. So each time we need to improve our impedance model and all this. What we don't know, nevertheless, is what is the necessary ionization cooling doing for collective effects. Because we have the expert here, Chris, mastering all this, but we don't know the interaction between the particle in this process. I have a student coming in October to work on this. And in particular, we would like to know what are the wake fields or impedance in matter. Because what I told you before, normally we have vacuum. Inside a beam pipe, we have vacuum, muons or particles are traveling there. And then due to the interaction with the beam pipe, which is maybe not perfectly conducting, not smooth, etc., you have the impedance. But now we have also cases where the particle will circulate not in vacuum, but in matter. So the first thing we can do is generalize the impedance we computed or derived analytically in the past by replacing the emissivity and permeability of vacuum by any emissivity and permeability, but it has to be done carefully. I started to do this here if you want to have a look, and it will be finalized with the student when he will come. But in particular, we need also to study what is exactly the effect of this ionization, and we can imagine maybe that a plasma could be created there. All this has to be studied in detail, and it is a new mechanism, hopefully not jeopardizing the project. I remind you that the new collective effect discovered in the LHC after project approval was electron cloud, still limiting the LHC. Now we are studying this before. Let's hope we have time to do this. I come now to the conclusions. So collective effects, I do hope now, who were aware of collective effects before this course? Nobody? So I do hope now that you know what collective effects are. And these collective effects become important and are really machine performance limitations when one wants to increase the beam intensity or reduce the emittances, transverse and longitudinal. And usually this is what you want to do to maximize the luminosity in colliders or to maximize the beam power for the fixed target experiment. I don't know, for ESS, for instance, we like 5 megawatt on target. The emittance maybe there is not so important, but it is the intensity. Or if you want to have a larger brilliance in the synchrotron light sources. Collective effects can affect the motion of single particles or the beam as a whole, in particular the center of mass, but it could be also the envelope, etc. It affects coasting beams or bunch beams, single bunches, many bunches, can be longitudinal, can be transverse. And it can be studied now these days with numerical tools such as X-Suite, which is really great, and there you have space charge, beam, etc. But as I said, even if you need now to study all the interplays between the mechanism, you need also to understand what you have. So the theory behind you need to understand. Because now maybe these days it's easier to put everything in a code, but you have to trust this and to check. Or you can study this also through measurements, beam-based or on a bench. Why do I say here on a bench? Because you understood here that a great activity is to characterize impedance of equipment. So sometimes now we take equipments on a bench in a room, and we put, for instance, a wire inside it. We put a current, and we look at the transmission and deduce the impedance, sorry. So this is why we can measure all these equipments. Ideally, this is what I said to my team for many years, I would like to do this for each equipment coming in the accelerator. And by the way, each equipment going away from the accelerator. You know, sometimes you exchange something because I would like to see the equipment when it is removed, which impedance I have to remove from my impedance budget. So you see, it's a huge work. You can study instability starting from single particle equation of motion or the more involved formalism of Vlasov equation or Fokker-Planck equation when diffusion and damping are discussed. And the collective effects can lead to beam losses, incoherent, so single particle, maybe on resonances, etc., or coherent, maybe the center of mass. It can be longitudinal transverse, and it can lead also to emittance increases in longitudinal transverse, either the core of the beam or the halo. So this is why you need to understand all this to understand, for instance, these pictures. Look, this is intensity per bunch as a function of number of turns. You inject, so it's flat, perfect, but after 11 turns, you see that you lose. You need to understand why you lose. This picture, I use it also for muon colliders because you see it is in the SPS at CERN. It's only 11 turns, so you can lose in 11 turns. If the impedance would be 2 times bigger, you would lose in 5 turns. So it's not because we are fast in muon collider that there is no instability. We have to do this carefully. This is an instability. You can measure the rise time. This is in frequency domain, amplitude in dB versus frequency. Why there are some lines which are growing here and how? This is a bunch which is unstable, and this is the center of mass, turn after turn. You superimpose. Why do you have this shape? Here, this is the vertical emittance as a function of the bunch number. You have trains of bunches in the LHC. So you see at the beginning of the train, the emittance is about 3 micrometers, and at the end, it's about 5. Why? Here also, superposition, fully symmetric. Here it is asymmetric, mainly in the head of the bunch. Why? Here it's mainly at the head of the bunch. Why? This mode coupling. This is stability due to Landau damping. Why and how can you lose Landau damping? So it is all this that you need to understand. So it's a lot of theory and work, but it's really a fascinating field. Last words. So we are here. I think I'm leaving here. And in the future, the proposed accelerator would be this FCC-E, 90 kilometers. This is the current proposal, let's say, for the future circular collider. And at the middle of it, you have Archamp and this European Scientific Institute, and in particular, the Joint Universities Accelerator School that I am leading. There we offer courses on accelerators, 10 weeks every year. So if you are interested, please join. You see, you will be in the center of the next accelerator, maybe. We can dream big, the ultimate colliders. I think this is what you want to discuss in a few weeks. There is the Fermitron around the Earth or the Plancatron around the Milky Way. But we need also to dream green. And this is not easy, being green, because we rely on electricity. Many thanks for your attention, and welcome to the fascinating physics of particle accelerators. I don't know exactly, but it was, but there should be a name. Yes, Ralf Assmann. He used it in some slides. Ralf Assmann is a German accelerator physicist working now in DESY.
On Planctron?
He showed, no, not on this.
We will investigate.
You will investigate, exactly.
Just a curiosity, if the electron cloud was known before the LHC was approved, can you do anything about it? Would have been very different, the machine?
Yes, because we limited so what is the issue now, yes, with this electron cloud? We have some beam screen, and so it was discovered a bit too late. Mitigation measures were put in place. By the way, yes, I have some pictures, but not in the slide, where in fact, you have a beam screen, stainless steel, it's the vacuum chamber, Inside there is coating in copper, but on the side you have some saw teeth, small saw teeth. Why? Because then the photoelectron will hit this and produce less electron. So this was one thing done. Plus, we rely on what we call conditioning. When the bunches are coming, they attract this electron. You have a cloud of electron, but then you continue, you keep it like this. And doing this over hours and days, the second emission yield goes down. And initially, we conditioned the machine like this. It's just at the beginning of the year, you have to do this, in particular if the beam screen was vented and all this. But the problem that we saw after the first shutdown is that some sectors at beam screen where the second emission yield could then go down due to some pollution, etc. We could discuss this in more detail, etc. But now the plan is to have vacuum, let's say, part of the vacuum chamber with a lower second emission yield. For this, for instance, you do some amorphous carbon coating. Why? Because then you measure in labs that the second emission yield is below 1.1 or 1 something, and which prevent from the buildup of the electron cloud. So this is what we want to do in the future for HLHC, or if we would build the machine now, we'll do this differently such that there is no buildup. As I said, it's linked to the second emission yield. But if we would not have this electron cloud issue, we could have had much more bunches in the LHC. The LHC is a great success. But we started in 2008. We had an incident. This can happen. But it took 8 years to have the design luminosity, because design luminosity was reached in 2016. Fortunately, we discovered the Higgs boson well before 2012. But 8 years is quite a lot. It means the difficulty of running such a machine. And it was used with a beam which was not spaced by 25 nanoseconds as requested by the experiment, but spaced by 50 nanoseconds. Why 50 nanoseconds? Because for this beam, electron cloud is smaller. We have less electron cloud created by this spacing, because it really depends also on the spacing of the bunches. And now we run with more than 2 times the design luminosity. It's great, but there are 2 things that we could not do yet with the LHC. First, we could not reach the design energy, 14 TeV, 7 plus 7. What we are doing is 6.8 plus 6.8. Why are we not going from 6.8 to 7? Because we would need to train or to quench let's say, the magnet many times. So this quenching, let's say, campaign will take a lot of time. So we think it's not so useful. There is no really push from the physics. But linked to electron cloud, we could not put the maximum number of bunches of about 2,700 of something. There is less than this. And this is due to electron cloud, because then we induce too much heating on the beam screen. And there, we need to remove the heat from the beam screen, and this is from cryogenics. But cryogenics is at the limit in some sector. So it's a limitation. Otherwise, we could even provide more bunches and more luminosity. Does this answer the question? Yes.
Speaking of electrons, what do you do when another one fraction of the muons decays into electrons? Is this expected to give a huge effect, right?
So you have some muons decaying, you mean in the collider?
In the collider, yeah.
Yeah.
Or in the accelerator as well.
This has to be studied in detail. For the moment, I did not study this. I think we wanted also to discuss some collimation, etc., but I think it's not so easy with muons. With the electrons, they will, so on one hand, they perturb already the detectors. Then I don't know exactly what this electron will do. What do you expect?
No, but I mean from the point of view of this collective beam dynamic effects.
No, but then this electron cloud is really a multi-bunch phenomena. Because if you have just one bunch of mu plus, let's say, and few electrons, maybe you will attract them, but you will not create this cloud. I think it's true. David, I think in Los Alamos, many years ago, they had a long proton bunch, and indeed they collected some electrons which were trapped in the potential well of the proton, and then you have a coupling between the 2 beams, and you have instabilities. Here they are not expected, but we have to check carefully all the, let's say, the parameter space. But for the moment, I think I do not expect something to happen. Yes?
So we worked out for like proton-proton collisions, we have Coulomb repulsion, magnetic repulsion versus say for E plus E minus or mu plus E minus, you would have attraction.
Yeah.
Does that do anything to get us more collisions at the same luminosity, or is it negligible?
No, so with proton-proton you have this repulsion, but it is small because of course we optimized it, we took this into account, so you have a small effect as you have a small emittance growth over hours. It's true that when you have E plus, E minus, or in this case mu plus, mu minus, I think Daniel Schulte has nice movies on this. When two bunches are coming, they are attracted. So there's a kind of a pinch effect, so it increases a bit the luminosity, indeed, yes, in the center like this. So you have a bit more, but then after there is a huge deflection, and then also the kind of a disruption because the beam can be destroyed. This is why above 3-4 TV, E plus, E minus, then the beams are almost destroyed. This is why also at 10 TV, E plus, E minus, people are saying it's for linear colliders or linear with plasma, etc. It's maybe not a great idea. But as I said, Daniel Schulte has very nice simulations for this. So on one hand, yes, to answer, a bit of enhancement, yes, this pinch effect, but then after disruption is not so great for the beam because then you have different trajectories and... You're welcome. Something else? No?
I have a further curiosity because
Please.
now you mentioned electrons. So when they do this nitrogen infusion in the cavities for the linear collider, they tell you...
Say it again. No? When we do what? Yeah.
They do this nitrogen infusion in the baking of the cavities for the linear collider. And the advertisement is that it gives you 50 megavolts per meter,
Yeah.
which is good. But now, after all you explained, they should tell me also how much it changes if it changes the impedance.
Sure.
Is there any number for this? Is it a question already investigated?
No, as I think as also Daniel said, also depending on the cavities, what also is important is this R upon Q, which depends on the geometry, mostly. But it's true that the cavities, they have to be optimized. And I have to check carefully also what the R upon Q will be, or what the Q will be, and all this. You're right, because it can introduce huge impedances. As I said in the LHC, with this crossing, we lose luminosity because of the crossing angle. So for HL LHC, what we will do is to have crab cavities, meaning that before the crossing, the bunches will go through some crab cavities, which will tilt the bunch, so that it will tilt, so that at the IP, there will be a full overlap. Not exactly full, because we had to reduce the crab cavities by factor 2 for some budget constraint. But ideally, it is this. But these crab cavities are introducing huge impedance. So for years, we were in iteration with our colleagues from the US doing this to reduce the impedance. Not only the impedance of the fundamental mode, but also all the high-order modes, because there are huge high-order modes which are created. I could have shown you pictures where you plot the impedance as a function of frequency and you have huge spikes. And this is, we ask to reduce all these modes. It's a lot of work. So indeed, if they improve cavity for some reason, there could be an impedance problem. I discussed during lunch also for beam instrumentation. If someone comes to measure something, put some equipment, it has to be optimized maybe to interact with the electromagnetic field of the beam. So there will be some interaction, and maybe it will perturb the beam. So this has to be checked carefully. So I hope you understood that we have also some challenges from the accelerator side, which is also very interesting and motivating. And yeah,
Thank you.
that's it. You're welcome.
Thank you very much.
Okay.